All right, so I've started the recording for this session. All right, guys. So what we're gonna do in this class is basically discuss about steels, and we'll start with steel making and how. Like, I won't spend a lot of time on this, but I feel like this is important for you to understand, like the basics of steel, and then we'll go into different grades of steel. I will try to cover as much as possible in 1.5 hour period. It's a lot of lecture notes here, but I'm not going to bombard you with a ton of information. Whatever we can cover in 1.5 hours, we'll just stop there. So, and remind me if it's 6:30 already once we start. All right, because I'm in the slideshow mode. I don't see the time on my laptop right now. All right. So generally, when we talk about steel, steels is an alloy. Any kind of steel is an alloy of mainly iron and carbon, and then you add some other impurities to it. But in general, if anybody says steel, that is, it's a combination of iron and carbon. And in steel, the percentage of carbon is less than 2%. To be precise, it's 2.1%, but we'll stick to 2% here. Now we add carbon to enhance the strength of the material, to make it stronger and harder. If you take pure iron, it is ductile and malleable, but you need something stronger, so you add carbon to it. Carbon is going to provide strength by going into the interstitial positions. I think by now you guys understand the kind of impurity addition positions that are present. You can have a substitutional impurity or interstitial. Carbon, being small in size, it goes to the interstitial positions, and then it makes the dislocation motion even harder for other atoms, and that's how it provides strengthening to the material. Uh, Iron, uh, you guys might be aware of this fact. Iron shows something called allotropy. So, 10 words. I'm trying to write it. Okay. So, iron shows something called, oh wow, it's not working that great.
Looks.
What I'm trying to write is allotropy, Allotropy. So, iron shows this form called allotropy. That means it has different crystal structure when you vary the temperature. So at room temperature, the iron that we are used to seeing has a BCC crystal structure, body centered cubic. If you increase the temperature to a higher value, it transforms to an FCC structure. And there's a phase called austenite that forms. And if you heat it even further, then again it goes back to the BCC structure. When we say BCC, that means you have a unit cell and there's one atom in the middle. So that is your BCC structure for iron. Most of the room temperature work for iron happens in the BCC form. And this is the strengthening that I was talking about. You can have strengthening via interstitial or substitutional alloying addition. When we add carbon, the main alloying element in steel, it goes to the interstitial position in between the atoms and provides strengthening. But let's say you have stainless steel. Stainless steel becomes stainless because of the addition of chromium, and chromium is really big. So chromium goes to the substitutional side. That means it replaces one iron atom and sits in place of that atom. And that's how it provides different properties. But if you compare the strengthening behavior, carbon is going to provide a higher strengthening than chromium in case of steel. So FCC, I think you guys are aware of FCC structure. You have atoms at each corner, and then you have one atom at the face center. I I assume you guys know these things, but if you feel like I'm rushing into topics or something, just stop me, ask question, feel free. Like, it doesn't have to be super formal class
Yeah,
right now.
yeah, you're good.
So yeah, if you have question, you can ask me. All right. So how do we get steel? Basically, the steel extraction is done from iron ores, which is basically dirt. So you get dirt and you're going to heat it up with some other additions. which is going to help you in purifying that dirt. That dirt from which iron is extracted is called the iron ore. And we take this iron ore, we mix it with limestone and something called coke. This coke is not the Coca-Cola. This is basically coke you get after after heating coal in the absence of air. In the anaerobic condition, if you heat coal, it transforms into a black. Well, coal is already black, but when you heat it up in the absence of air, all the impurities which are present, they are removed, and whatever you're left with is called the coke. So you use coke, it provides the heat source and some reducing agent. And then we have limestone, which acts as a flux to separate the impurities from the molten metal that we are going to get. So you take iron ore. These iron ore are basically, it's an alloy. It has a lot of oxides. Some of the used alloys for iron ore, iron extraction is hematite, magnetite. These are different kinds of rocks or the dirt soil that we get. You heat it up to a really high temperature, use coal and limestone and extract iron, and the impurities that are present, they get separated out. And this whole process takes place inside a furnace. That furnace is called the blast furnace. So as I told you about coke, you don't have to know the details. You don't have to remember this so much. Limestone, it acts as a flux. You add that, and basically it's going to act as a sponge and separate out the impurities which are present in the material. This is the reaction that takes place inside. Since you have added a lot of coke, which is a form of carbon, so this carbon reacts with oxygen and forms carbon dioxide, and this carbon dioxide reacts with excess of coke and forms carbon monoxide. And coke and carbon monoxide both act as the reducing agent. So the reaction that takes place inside is you have an iron ore, which is an oxide of iron. It reacts with coke, and that's how you separate pure iron. And then the excess of carbon monoxide that you have, that also reacts with your oxide, and it also reduces. Since you're reducing iron oxide to iron, that's why it's called a reduction reaction that's happening inside the blast furnace. The blast furnace setup looks something like this. If you were standing next to this blast furnace, you would be this big. That's the, just to give you a sense of scale. These structures are giant, and you put all the raw agents, elements from the top, which is your coke and iron ore and limestone, and then it gets heated up in the chamber, and then it's separated from the base of the structure. You get pure material, hot iron, in a separate car, and then there's some impurities on the top. That impurity is called slag. That impurity is separated out, and it goes to the cement industry. They would use it for other application. We are mostly focusing on the iron side, the pure metal that we extract. Now the iron that you get out of blast furnace is called pig iron. It's not steel yet. It is called pig iron because it has high percentage of carbon, and it is not super pure. So it's really brittle, it can break easily, but we purify it further and we get steel after that. This is how it looks like, the pig iron. Now for steel making, this was the pure iron. From pure iron, you are going to do some more refining. That refining can be done in a furnace. It can either be a basic oxygen furnace or something called electric arc furnace. So what you do is, like, either you take the molten metal and put it in this furnace and heat it up again, or you just take the molten metal itself, put some alloying elements, and then you try to remove carbon. So what, we had excess oxygen to start with. We reduced it. Now the iron is pure, but now we have more carbon. So we have to get rid of that carbon. So you again put oxygen and oxidize it to get rid of carbon, because carbon has more affinity for oxygen and it will form carbon dioxide, carbon monoxide gases. So in a basic oxygen furnace, basically there's a big ladle, and the ladle you put your material, the molten metal, and with this big LAN system, you are going to purge oxygen at supersonic speed. really fast. And this mixes the material completely, and you add some limestone as well, and that's how you can purify it, make the material like the pig iron has 3 to 5% of carbon. But after doing this processing, depending on what the customer needs, you can reduce the carbon percentage to less than 2%. You can have less than 1% or 0.5%, depending on what's the requirement. And this is the step where you will be adding some alloying elements. If you want to make, let's say, stainless steel, you either add those alloying elements at this step, or there's another step, secondary step that you do. This is where you determine what grade of steel you want to make. So this is basic oxygen furnace, and you're purging oxygen from the top. Again, you'll form some impurity which gets separated on the top. It is called as slag. You remove it, and from the bottom you'll remove the pure steel that you get. Uh, in this, you can either use scrap steel, recycled steel, or the steel which is coming from the blast furnace. This is the sense, just to give you a sense of scale, if you were standing next to it, you would be this big. So these structures are giant, really huge. And this is one of the ladle through which your pig iron is being poured, where you can do the purging of oxygen. Similarly, we have electric arc furnace. I won't go into the details, but in this one, you can provide external heat because you have 3 electrodes. You have big giant electrodes, and they will touch the scrap steel and move up slightly. So it creates an arc, and this heats up the material. So most of the steel plants that do not have a blast furnace, they just get scrap steel, generate electricity. That's how it heats up. Now you have metal in the molten form. You add whatever alloying elements you want to add. You add some limestone to purify it further, and then you do oxygen lancing, and that's how you clean your pig iron to a purer form of steel. So you can either do basic oxygen furnace or electric arc furnace. This is they generally use 3 electrodes, so that's how the screen would look like if you are the operator or the engineer in charge of running this plant. This is how it looks like. It's also giant, and like this also gives you a sense of scale, like how big these structures are. Here's some of the electrodes picture. We don't have to be worried about that. Now, once you get the steel, either you can take the steel and put it in big ingots, which is called ingot casting, or there's another process called continuous casting. You can do continuous casting and get sheet form of material or plate form of material depending on your need. This ingot casting is outdated. People don't use it anymore. They stick to continuous casting because that's much more efficient way, and you get better produce when you do continuous casting. So if you look at this is just one step of tapping. Tapping is basically the step of removing molten metal from a furnace. That's called tapping. There's some pictures for ingot casting. I won't go into the details of ingot casting, but I'll give you a small idea. When we do ingot casting, what can you do? You can just have a mold. You get the molten metal, you pour it in a structure, in a mold. This is a mold, and this you are pouring the molten steel. What happens is, if you are not doing any special treatment, you will get a lot of porosity which are present in the material, and there will be some chemical segregation. Some of the alloys might start to segregate out, and you will not have a homogeneous composition. This is called rimmed steel. This is an ingot type of casting. You can get rimmed steel. This is useless, very cheap method, but useless. You don't want to use it. If, let's say, you are doing ingot casting, you can put a cap on the top while it's cooling down. In that way, it creates a pressure difference, and it helps the impurities from not segregating out so much. This is called a capped ingot casting. It's helpful, but it's still not the best one. Then there's something called semi-killed and killed steel. Basically, when you get steel, and in that steel, if you add aluminum or silicon, If you add these two elements, what it does is it helps the gases to escape out easily. So if you have a killed steel, that means you have added a lot of aluminum or silicon, you will have a homogeneous structure which can be used for any purpose. Or if you add, let's say, one of these, you don't have a lot of money or you don't care about huge amount of purity, then you can just add some amount of either both or one of these, and then you get something called semi-kill steel, which mostly is good, but it has small bad part, which you can just chop off and send it back for steel production again, and you can use the part which is good. So these are the types of steel that you can get from ingot casting. These days, people don't do ingot casting. Most of the time, they are using the killed steel. That means they'll, instead of solidifying it, they add aluminum and silicon, and then they proceed for something called continuous casting. And that's how everything is done these days. These are the details, exact same thing that I spoke right now. So we can just skip these slides. All right, so now is the time for continuous casting. That's something which is used in the industry these days. In continuous casting, what we do is we are going to slow down the steel very slowly in such a way that we can give it the shape that we want while it's slowing down. For continuous casting, the starting material is a killed steel. That means you have added aluminum and silicon. And when you do this, you can either form billets, blooms, or slabs. These are different names based on the dimension of the steel that you're producing. Now, when we do this operation, the steps involved in this are shown here. So let's say you have, let me show you this figure here. Yeah. So this is your ladle at the top, right? We're doing continuous casting. This is your ladle. And then you have something called a tundish. Tundish is basically, you can think of it as a funnel. It acts as a funnel, which helps you to pour this steel. There's a nozzle, it's called submerged entry nozzle, which goes to a mold. You have a copper mold. So they use copper mold because what they want is as soon as I pour it, the surface should cool down so that it makes a really strong outside layer, whereas the inside of the material will still be in the molten form. So you have a copper mold, there are a bunch of rollers, and there's a pendulum shear. I'll explain you what that does. So how the process is done is you have a starting rod which comes in, which is going to draw the molten metal. You have your molten metal in the ladle here. It is poured into the tundish. It comes here. Now from the tundish, it'll go to the mold. It comes here. Then with the help of rolls, it is bent slightly. And then once you have got the length of this slab or plate, whatever you're making, if you have determined this is how long I want the material to be, you determine that length, and then you use a shear, pendulum shear. You can just shear off the piece that you want, and it can go on for further use. So this process just continues. You have two ladle holding heads here. So the tun dish acts as a reservoir, and then you can switch the ladle. So that's how the processing is done. This is the same continuous casting. Uh, when you do continuous casting, it saves time, it's faster, and you can have multiple streams of molten metal coming outside. And you can make a lot of things, billets, blooms, slabs, sheets. So after doing this processing, sometime the customer might want something really specific. And that's where secondary steel making comes into picture. I'm not going to discuss this because I just wanted to give you an overall view. But let's say you want tool steel to be made or some other kind of steel which is like very unique. uh, they will use some kind of secondary steel making to purify the material even further. And that's where vacuum degassing and all these different kinds of steel making processes are used. So I won't go into the details of these processes. If you want, you can read it later, or if you want, you can contact me later on and I can give you more information on that. That's how the processing is done. From here onwards, I'm going to move on to uh, something which would be more interesting to you guys, and that is understanding the solidification and the phase diagram. Where's that slide? Yep, this one. Do you guys have any question on the initial part that we discussed till now?
No, I think the main thing is yeah, like the phase diagrams and stuff that you're about to
Yes.
get into.
Yeah. Yeah.
That's the meat of the stuff we'll need.
That's true. Yeah. It's just good to have background information because
Yeah.
that'll help you guys to understand it even better. All right. So now we got the molten metal, and you generally store it in some container, and it solidifies. So basically, solidification happens, which is a process of liquid metal transforming into a solid. Now, this solidification process can occur either via heterogeneous or homogeneous nucleation. When I say nucleation, that means a small grain will start to grow, uh, and then its size increases and forms a grain. So the solidification process has two steps of nucleation and growth. Now, in general, I think you guys would have covered homogeneous and heterogeneous nucleation, so I'm not going to go into details of that. But let's say you're looking at the heterogeneous nucleation. You have some nucleation sites, and that's where the grain starts to grow in different orientation. So these are grains which are growing in different orientation, unit cell. Now the growth starts to happen. It keeps on increasing as you cool down the structure. As you cool it down further, you'll see it reaches a stage where it cannot go further. It will meet up the next unit cell. And when that happens, that's the region which forms something called the grain boundary. So you get the formation of grain boundaries. Grain boundary basically means if you cross that region, you will have grain of different orientation. Now, grain boundary is a really high energy region. So that's why if you're working with metals, you have different grains. If you do a step of etching, let's say you polish and then you're etching it, you can reveal the grain boundaries easily because if you look at the surrounding of the atoms in the grain boundary is not stable. They do not have equal neighbors. So they are in a high energy state. If any chemical attacks, it will attack the grain boundary first. And if you look at inside of the grains, the neighbors are really organized and everything looks nice. So that's why whenever you do etching, it's always the grain boundary which gets attacked first. If you do over etching, that means if the chemical is exposed for a longer time, then only the complete material reacts with the solution that you're using. So grain boundaries plays a really important role, and it can define a lot of properties depending on if you want something really strong compared to, let's say, something ductile. Grain boundaries is something you should be playing with. And when you do different kind of heat treatment, you can actually change the grain size. So if you want something stronger, in general, small grain size is something which is desirable. So when you do casting, a lot of time you make, like for this project, I think we are supposed to do casting. If you do casting, the grains comes out to be really big. So if you control the parameters slightly better, you might be able to reduce the grain size. That will help you to get a much better hammer out of whatever material you are working with. Uh, this is just some examples of how big a grain can be compared to how small. Like these grains, which you see here, these are of centimeter scale, whereas these grains that you're seeing here, they are of the micron level scale. So depending on different processing condition, you can have grains which are really big compared to grains which are really small. Now, when we freeze a material, let's say you're cooling something, solidification. So what you know in general for ice is you have water, or yeah, you have water, you cool it down, you reach 0 degrees centigrade, and it melts, it solidifies and forms ice. If you're working with any pure material, it will have a melting point. So for example, the figure shown here, you have molten form of metal here. You start cooling it down, nothing happens. As soon as you reach the melting point, it will start to convert into solid. It solidifies at that temperature completely. At that moment, you won't be able to see the heat. It is called the latent heat. And then if you cool it further, then complete thing is like solid. So in case of pure metal, this process happens at one particular temperature. A lot of time, if you want this kind of freezing to happen, it doesn't start at melting point. You need small amount of undercooling. You have to cool it further, and then you get enough energy that it starts to solidify. The point at which the solidification happens is called the liquidus point, and the point at which the solidification is completed is called the solidus point. Most of the liquid needs to undergo an undercooling or supercooling, that you cool it further, it's still liquid, and then after a certain time it starts to solidify because it needs that extra energy for nucleation to happen. Now this is what happens in pure metal, but we generally work with alloys or mixture of material. So in a mixture of material, the freezing will start at a point, and then instead of having a melting point or freezing point, you have a range. The temperature decreases, and in this region you'll have a mushy zone. It'll be a mixture of liquid and solid. And then at a lower temperature, the solidification completes. So you can see in case of alloy, you have a mixture zone as well. Instead of a one point, you have a range, melting range or freezing range. This same concept is used to form the phase diagram. So let's say you have pure A on one side, and this is the melting point of pure A, 520 Fahrenheit. And then you have B on the right side, and there's the melting point of B. Now, if you take a mixture of A and B, you will see that it gives you a range of melting point. As soon as when you change the composition of the mixture, the range varies, right? Now, if we make it nicer and connect these dots, connect them something like that, then you'll get an overall idea that for what composition, what kind of range, temperature range I'm getting. So if we make it clean, it looks something like this. Now let's clean it even further. We have temperature on y-axis and composition on the x-axis. And let me remove the thermometer. And this is what you get. This is called the phase diagram. You have liquid on the top, solid at the bottom, and in the middle you have liquid plus solid region. You guys must be aware of this thing since you took the basic material science course. The line here at the bottom which separates solid from liquid solid is called the solidus line, and the line which separates liquid from liquid solid is called the liquidus line. Uh, there are some definitions. You guys are aware of this. I'm not going to go into details of these definitions. This is an example from the Callister book itself. It's the same example. You have liquid, solid, and the middle you have a mixture zone. These kind of diagrams are called a binary isomorphous system. It's called isomorphous because it is completely soluble. Like one component is 100% soluble in the other component. Apart from this, there's just an example. Now we have something called a binary eutectic system. In eutectic system, basically a liquid, instead of going into a liquid solid region, it transforms into a solid region. That mushy zone is not it is not existent, only at a certain point. So that point is called your eutectic point. That's where that reaction happens, where one liquid goes into two solid forms. Excuse me. So you have liquid, it goes into two solid form. That's called the eutectic reaction. I'm sure you guys must have seen plots like this, where you have one solid region here, another solid region here, then you have solid in the middle. And this is your eutectic temperature. So the top line is liquidus, solidus, and these lines are called solvus. It separates one solid from the other, right? And then we have eutectic. This is just an example of lead and tin system, and we'll move on to like you guys have basic understanding of this, how solidification happens. Let's say you are in the liquid zone here, everything is liquid. As soon as you start solidifying, part of the material solidifies and part is liquid, and if you keep on solidifying further, you form different phases. So I'm sure you guys are aware of this. So from here onwards, we'll move on to the main discussion that we need to do, which is the iron carbon system. This is your iron carbon equilibrium diagram, or also called the iron carbon phase diagram. It is called iron carbon, but actually it should be called as Fe and Fe3C phase diagram, because we are not looking at the carbon composition up to 100%. We look at carbon composition up to 6.67% only, and iron and 6.67% carbon forms Fe3C, cementite phase. So this is the iron carbon phase diagram without any information on it. I'll just quickly show you what are the important components. You have a temperature 1341. The temperature is in Fahrenheit here. Then there's 1414. That's another important temperature. You have 1674, 2098. Then there's the temperature axis. Then we have some important composition of carbon on the x-axis. Up to 2%, it's called carbon steel. If you have carbon more than 2%, it's called cast iron. So that's a huge differentiating point there. You don't want carbon percentage to be really high if you're aiming to form steel. The top region is your liquid region, and you have the liquidus line, you have the solidus line. This is the eutectic temperature where you have liquid and it transforms into austenite and cementite. Few phases. Then you have the solvus line. All right. Are you guys aware of the ferrite, austenite, and cementite?
Um,
Yes.
All of you?
Yeah, yes, but I wouldn't say I know everything about them in this situations. If like I couldn't tell you what other elements do what to ferrite and austenite, cementite.
Okay.
I couldn't tell you like.
Okay. Yeah, I'll just briefly go over this for now. For example, so I'll explain you once we reach there. So we have I showed you some of the phases. Now there is one small region. This is called the liquid plus austenite region. This complete is austenite. When we say austenite, basically a pure austenite shows you iron, Fe. This iron is in FCC crystal structure. That is the austenite phase of iron. Now, if you look at this diagram here, if I say pure iron, it should be just this line, right? But if it's going further here, that means iron can dissolve up to this percentage of carbon. So that's the maximum percentage of carbon that can be dissolved in this phase. FCC iron does not show magnetic properties. Iron has magnetic property up to a certain temperature. That temperature is called Curie temperature. FCC phase does not show the magnetic property. And if you want to form the phase called martensite, which I'm sure you guys would have heard that phase, you have to heat the material to austenite region. This is something very important which you guys should know whenever you are doing heat treatment. Let's say whatever steel you have, you want to form martensite. You should heat it to the temperature so that you form austenite. And that's where the phase diagram comes really handy. If you have a lot of alloying element, you have slightly different phase diagram. But you look at the phase diagram, you know where my austenite is, you heat it above austenite, up to austenite temperature, and then you decide how fast or slow you're gonna cool it down. So this is the FCC structure, which is iron. Austenite and liquid are at the edges, like you have austenite here, this is liquid. So whatever region is in the middle, that will be liquid plus austenite. Similarly, this region here, if I can highlight, this small triangular region, That is ferrite. It's called ferrite, or you can call it the alpha ferrite as well. It's called alpha ferrite too. That region has BCC crystal structure. And now you look at the difference, what I was saying. You see for austenite, the maximum carbon that can dissolve is really high, 1.7%. But you look at ferrite, the maximum carbon that can dissolve is really small. This number was not important for the class I was teaching, but if you guys want to know, that comes out to be around 0.02% carbon. That's the maximum carbon that can be dissolved in ferrite. So ferrite, not a lot of carbon can dissolve, and it is in BCC structure. All right. So that's the ferrite phase. That's how ferrite structure would look like. It doesn't have a lot of features. It's a pure material. If you had more amount of carbon, then it would be visible in layer formation. Now the region below this here, this is your ferrite. So you have ferrite phase here, and this dotted line, which I was showing, that line shows you a composition called pearlite. Pearlite shown here. Pearlite is not a new phase, it's just a name given to this composition. Pearlite is basically a mixture of ferrite and cementite. How do I know that? I don't have to remember it. There's nothing to remember on this, right, except like knowing this diagram. But if you're confused, let's say for pearlite, how I name that phase is pearlite is this composition here for this part. So what you have on the left, you have ferrite. What you have on the right, you have cementite. So pearlite basically is a mixture of ferrite and cementite having a constant composition. That's all what is there in pearlite phase. This is how the structure would look like if you are having a pearlitic steel at that composition. It is in the form of layers. You have one layer of ferrite, one layer of cementite, and that's how it goes. So that's how it looks like. This is the pearlite phase. Uh, there's the ferrite. I already told you what ferrite is. This reaction here is called eutectoid. So the reaction that I told you earlier was eutectic reaction, in which one liquid will transform into two solids. So in this case, this liquid which you have at the top, it transforms into two solids, austenite and cementite. In eutectoid reaction, you have one solid and this transforms into two solids, two different solids. In this case, we have ferrite and cementite. So that's how the transformation is happening, and this reaction is called the eutectoid reaction. There's the pearlitic dotted line. It was important for the class, that's why I have it dotted there. This region is your austenite and cementite, which makes sense because you have cementite on this axis. If at any point you guys have confusion in the iron carbon phase diagram, just speak up. I might be assuming few things. If you don't know, don't hesitate, just let me know. I understand this can be a lot of information because you are studying a lot of other courses too. So if you're confused, just stop me and let me know. All right, so then we have this pearlite and cementite region, and that was the liquid and cementite region. Now here comes the most important line of this phase diagram. All these other lines are important, but since you guys will be doing heat treatment, in order for you to understand at what temperature I should be doing the heat treatment, there's a line which is called the AC3 line. If you're doing annealing, if you're doing hardening, mar tempering, os tempering, any kind of heat treatment, you have to take into consideration the AC3 line. This line has been given a name because it's important, as this line shows you where you are going to start forming 100% austenite. So let's say you have a steel which has a low percentage, less than 0.8% carbon. You want to heat it up and then form martensite. So in order for you to be able to know at what temperature I should be heating it up to, just refer to the AC3 line, because as soon as you cross AC3 line, whatever material or structure you had, that gets transformed to austenite. Now you're in austenite phase, and then you quickly cool it, you'll form martensite. The way I used to tell in my class is just remember the ANM acronym, because A&M is like austenite and you transform to martensite. So if you want to go to martensite, you have to transform everything to austenite. So AC3 line becomes really important. If you're working with high composition of carbon, then there's no way to get rid of cementite. So the AC3 line comes till here. So as soon as you heat it above this temperature, you get austenite and cementite, and then you do other kind of cooling process. So AC3 line is one of the most important line for heat treatment understanding. Then you have another line called AC2. You won't be using this line a lot, but basically this line tells you the temperature above which steel becomes non-magnetic. AC2 line is the Curie temperature line. So Curie temperature is the temperature at which it's called like this, Curie's temperature. This temperature is the temperature above which steel becomes non-magnetic. Any steel, it will be non-magnetic above this temperature. Then there's another important heat treatment line called AC1. This line basically just tells you the onset of austenite formation from the perlitic region. Sometimes this line is referred in the text as well. So just having an understanding where AC3 exists, AC1 exists, it's important. And now in all these three lines, you would have seen that this part is common. So this is called your AC1 to 3, like all the lines are there. So AC3 will be the one which you guys should keep in mind. AC2, if you forget, that's totally fine. That's not a big deal. And then there's another line of ACM, which basically shows you the separation of austenite from an austenite and cementite phase. So you might come across these terms in the text, and that's why understanding this is really important. These lines basically come from the French words. I don't know like exactly. I think A stands for arrêt, which means temperature arrest or something like that. So that's where these lines come into existence. Okay, and then there's another iron. As I was saying, iron transforms from BCC to FCC and then again back to BCC. So this again back to BCC is referring to delta iron. The ferrite shown here at the bottom, that is called alpha ferrite. Then you have austenite, and then you have delta ferrite, either delta ferrite or delta iron. Not an important phase. Whatever is happening in this region, most of the time we don't deal with it because then you have partially liquid metal. You don't have to be concerned about the delta iron region so much. So we'll just look how it looks, but you don't have to worry about this small triangular region. All right, if you are in the region to the left of eutectoid temperature, it's called hypoeutectoid region. If you are in the region to the right of eutectoid temperature, that's called your hypereutectoid. This hypereutectoid is valid up to 2% because after that you have cast iron. So if you're in the cast iron region, if you're to the left of eutectic, it's called hypoeutectic, and if you're on the right of eutectic, it's called the hypereutectic. So that completes the iron carbon phase diagram. Some numbers might not be what you see in the literature because those numbers vary depending on what system you're looking at. Like for example, I've shown here 0.8. Most of the book shows this number to be 0.77% of carbon. And here I have 2%. Most of the book shows this to be 2.1% of carbon. So a small variation will exist, but the basic structure of an iron carbon phase diagram is like this. So on the microstructure I showed you, so we don't have to go in the details of these microstructure. This is just showing you like a different composition, what kind of structure you can expect in the material. If you need details on this, you can discuss with me. I'll give you much better images than the old images that I have here. I already talked about the institutional and substitution solid solution. This is just some of the heat treatment process that is done. So we can quickly move past this. Yeah. So now if you are doing, let's say, heat treatment, whatever grain structure you have at the room temperature, let's say you got a sample from the TPM guys, whatever structure you have at room temperature, if you want to change the grain size or make more modifications, just doing the heat treatment can help you change the properties a lot. For example, if you have one grain size, but if you heat it up, you are heating it up, as soon as you cross the AC3 line, it doesn't matter what structure you had in the initially, the grain size is going to change. If you are just above AC3, the grains will be small. There won't be any grain growth happening. But if you are not careful and if you heat way above AC3, then grain growth starts to happen. So you have to optimize the heat treatment that you are doing so that you don't increase the grain size a lot, because that will be detrimental for the application we're looking at. So that's how temperature affects the grain size, and you have to be careful. And this is something which we can discuss depending on the grade of steel that we decide to go forward with. Okay, so that was the iron carbon phase diagram part which you'll be using. Most of the time, you will be doing some kind of heat treatment on your steel. No matter what grade of steel you have, we will be doing some kind of heat treatment to get the optimum property. Now, the basic heat treatment that people do in a steel is shown here in the slide. This dotted line that you see, this is your AC3 line. So any steel, just focus on the AC3 line. You can do something called annealing. When you do annealing, you're going to heat it up. Heating rate is not very critical. It is critical, but it's not the decisive factor. You can have a decent heating rate, that's fine. Then for how long you want to do the heat treatment, let's say we are doing annealing, we'll heat it up above AC3. And then for how long you are doing this, that's something which you should know. In general, industry uses, I think they use like uh, 1 inch per hour of heat treatment, something like that, depending on the material. So if it's 1 inch thick, they would do the heat treatment for an hour, or depending on the thickness. And it depends what your end goal is. So it varies. Then once you have reached above AC3, if you do a slow cooling, with slow cooling, there are 2, 3 kinds of slow cooling that you can do. You can either take out the sample. No, you can keep the sample in the furnace and just turn off the furnace. That's a super slow cooling, furnace cooling. That gives you certain properties, annealing process. You can do a slightly faster cooling by taking out the sample and just letting it cool at room temperature. It's also called normalizing sometimes. It's a part of annealing process itself. Or you can do a fast cooling, which is called quenching. You take the sample and put it in the water or oil, depending on how fast you want your cooling to be. If you are doing annealing, you don't want to do fast cooling. But let's say you're doing another cooling where you need hard material, stronger material and better properties. Then you can do quenching. So annealing does not give you super strong or super hard material. If you do quenching, you heat it up, go above AC3, and then quickly cool it down. That gives you a really hard and brittle material. So it makes the material hard, but your material will be brittle. So in order to make the material normal again or reduce the brittleness, you do a second stage of heat treatment, which is called tempering. So you're going to heat it to a slightly higher temperature, let it sit there for some time, and then slowly cool it. That's called the tempering treatment. Now, you can do stress relieving heat treatment as well. In stress relieving, if you have a material which has a lot of stresses present, if you're doing some kind of processing, you can do a heat treatment to a slightly higher temperature, but below AC3. You don't want to cross AC3 because then the grain structure changes. So that's called stress relieving. I don't think we need to do that, or we might be doing that if knowing what kind of casting technique they have used. So we might do stress relieving if it's needed. There's another kind of heat treatment which we will not be doing for sure. This is a long time heat treatment. It's called spheroidizing. It converts the martensite into spherical form. we will not be doing that treatment. There is some important heat treatment that you can do is os tempering and mar tempering. Basically, it's a two-step heat treatment. You're going to heat it up above AC3. You can quench it to a middle temperature. Let's say you heated up the oil and then you're quenching it up to the oil temperature and then you cool it down further. Or you can quench it and then stay at a high temperature for some time and do a second quenching. Os tempering and mar tempering, they give you different properties depending on what's your requirement. As you can see, the name mar tempering is related to martensite formation, and it depends on what is my MS temperature. The MS temperature shown here, this basically shows you when martensite starts to form. And os tempering is basically done in the austenite region, so that's why the holding temperature is slightly higher compared to the mar tempering. If you will need to do these kind of tests, we can see what's the material and what heat treatment we need to do. So this was like really basic information on the heat treatment part. I have some more information on the heat treatment, which will be helpful. And then we'll move on to certain grades of steel. You guys don't need this information. This is just a repetition. So let me move ahead. Okay. So depending on what is our requirement, there are different kinds of heat treatment that we will be doing for the steel that we get. If you want to make the steel hard and strong, there are some hardening heat treatments. By just changing the way you are heating and cooling, you can actually get different properties in steel. It's really interesting. You can get hardening, you can get softening, or people do conditioning as well. In hardening, hardening mostly involves either quenching, like you go to the austenite temperature and then you quench it. That will make the material hard. Or you can do some kind of heat treatment, which will be like you do a case hardening, in which case you're going to put a lot of carbon in the outside and then you heat the structure. So the carbon is going to diffuse inside your steel on the layer, which will make the casing of the material strong, but inside it remains fine. That's something which you guys might want to look into when you're working with this project. But remember, if you are diffusing a lot of carbon outside, let's say for our hammer design, if this is the piece and we surround it with a lot of carbon outside, what's going to happen is there will be carbon diffusing up to, let's say, this much depth. So outside this region will become hard for sure, and this will remain like normal it was. But if you're making something hard, remember it's becoming brittle as well. So something that you guys might want to look into is, if I do carburizing heat treatment, how it's going to impact my impact strength. If the impact strength is going down, or if this is becoming really brittle, then you don't want to do carburizing. So just think about those things. There's something called nitriding as well. So instead of adding carbon, you can add nitrogen on the surface. That also gives you some nice property. So that's some kind of heat treatment that you can think of doing. Then yeah, so if you do a heat treatment where no carbon diffusion is happening, that is called the diffusion less heat treatment. And if carbon diffusion is happening or nitrogen diffusion is happening, that is called the diffusion treatment. Uh, there are a few other heat treatments as well, which I'll show you in the coming slides. And then we have recrystallization. So this was the hardening section. Now you might want to do some kind of softening heat treatment as well. If your material becomes too brittle, let's say you're doing quenching and now your material has become really brittle. So you want to soften it back to normal brittleness. So you can do annealing. I already told you about the annealing process. And then you can do tempering. Tempering is generally done when you do hardening, which I was talking about in the previous slide that we had. So you can do these kinds of softening heat treatment. And then there's conditioning, where you just want to, you don't want to change a lot in the property, but you just want to get rid of some of the properties which exist. Like you can do stress relieving, you can do a low temperature treatment to get the desired property. So these are some of the heat treatments that's done in steel. I already discussed about this graph here. And I'm not talking about this rolling extrusion and forging because we are dealing with a cast material. We are not allowed to do any kind of mechanical working on the material. So I won't go into the details of these. Annealing, I already explained you that you heat it up that temperature. So yeah, when you do annealing, uh, that is a slow cooling. Now, depending on how you are changing the cooling rate. Now, so the basic thing which I'm going to explain from here onwards is how the microstructure gets affected when we do different kinds of heat treatment and cooling. Because how do you know that if I'm doing slow cooling, my material is going to become soft or is it going to become strong? It all depends on the kind of microstructure that we are getting after doing this kind of heat treatment. So when you do a slow cooling, you heated the material and then you just turned off the furnace once you are done. That is called your furnace cooling. When you do furnace cooling, you will form a phase which is perlite. Obviously, it depends on the composition, but generally when we discuss steel, we are near about the pearlitic region. So you form coarse perlite whenever you are doing furnace cooling. When you do, let's say, air cooling, this here says quenching, but it's like air cooling, you can form fine perlite, a finer size perlite. You can do forced air cooling as well, where you just use a fan to cool it even further. You can quench it in water, or you can quench it in oil, or you can quench it in salt water, which is the brine quench. That gives you even faster cooling. Depending on how quickly you are cooling, you can form perlite or you can form martensite. When you do quenching, you form martensite. Or there's one more phase which is called bainite. You can form bainite as well. Bainite is the phase which in general people don't discuss about much. But from research point of view, bainite can become helpful in some of the properties that we need. I won't discuss the bainite phase a lot in this presentation, but maybe next time if you want, we can go in the details of bainite. Now, one question you guys might have here, or if you know it, that's even better, that there's a phase which I was talking about is martensite. But that martensite phase is not visible anywhere in my Rn carbon phase diagram. And that's because this phase diagram is showing you everything at equilibrium condition. So everything is happening super slowly. If you heat up something and you are cooling it down really slow, then you form perlite. But if you are doing quenching or something fast, that is not visible on your iron carbon phase diagram. Iron carbon phase diagram just shows you the equilibrium phases and equilibrium processes. Martensite formation is does not happen at equilibrium stage. You have to do a really fast quenching or cooling to form martensite. Martensite is not an equilibrium phase. It is something called a metastable phase. It's metastable because if you leave martensite at that temperature for a really long time, like hundreds of years, it will transform to perlite and other phases. So martensite being a metastable phase and it forms at a really fast quenching, that's why it's not visible in the iron carbon phase diagram. But martensite is one of the most important phases that exist. So we'll discuss how martensite forms as well. Uh, why martensite is forming. So let's talk about that. Now, if you look at the phase diagram, you have austenite, right? You go in the austenite and you have dissolved 1.7% of carbon here. A lot of carbon is dissolved, all right? Now, let's say when you cool down from austenite, the phase changes to ferrite. Now, how much carbon can ferrite have? Maximum is 0.02%, all right? So in austenite, we have 1.7% carbon, and in ferrite, we have just this much carbon. So what's going to happen to all the other carbon that we have? It cannot stay in ferrite. So the phase which are present, the carbon which is there, it will diffuse out. It cannot stay in austenite because austenite is getting destroyed. It cannot stay inside. It will diffuse out. So you will form ferrite, and whatever extra carbon is there, that goes into the cementite phase. And that's how you have ferrite and cementite into existence. Now, in order for this diffusion to happen, you need to give the system a lot of time. And that's why you do slow cooling. So you can form this ferrite and cementite phase. Perlite is basically ferrite and cementite. Now, if you don't give this time for carbon to diffuse out, what's going to happen? You have an FCC structure, which is the austenite. You want to form the BCC structure, which is the ferrite. You did not give carbon enough time to diffuse out. So carbon will just get stuck in a middle structure. Now the structure you have with iron and carbon is not FCC, is not BCC. It's stuck in the middle, and that structure is a distorted structure. It's called BCT, body center tetragonal. And that structure gives rise to the phase called martensite. It's not austenite, it's not ferrite, it's somewhere in the middle. It's a metastable phase, and it's called martensite. And this phase formed because the carbon didn't get enough time to diffuse out, and everything just froze. So that's why you get the martensite formation. Martensite is a really brittle phase. It's a really hard phase. Most of the time, it makes the material super strong. And that's why we need to do quenching to be able to form martensite. The temperature at which martensite starts to form is your MS temperature, martensitic start temperature. And when it finishes, it's not shown here. It could be at a really low temperature or somewhere here. It's called MF. That is your martensite finish temperature. That's when martensite formation ends. So this plot here just explains you that how diffusion is happening and all. If you don't allow diffusion to happen, you just get a distorted martensitic structure. So depending on if you guys want to form martensite or not, you can do the heat treatment. Generally, martensite is helpful. And if you do quenching, you're forming martensite, you have a brittle material now. Now, if you want to get rid of that brittleness, you can do a tempering, a second heat treatment. Do a tempering, heat it to a slightly lower temperature than AC3, and then you cool it down slowly. So then it helps you to diffuse out some of the carbon and have a structure which is stress free, and then you have the ductility which is restored. So when you do this kind of heat treatment, let's say here I've shown you one example of carbon steel. It has 0.4% carbon. Now, depending on the tempering temperature, let's say you did quenching, and now you're doing the second heat treatment step of tempering. So how the property changes in general. If you increase the tempering temperature, the tensile strength keeps on decreasing, but your impact strength increases. So now for the hammer application, depending on what property is important to us. If we are doing the heat treatment, let's say we quench it after heating it up beyond AC3, quench it. Now we want to do tempering. How are we going to determine the temperature? Looking at these plots can help you a lot. If you want high impact strength, you know that you would have to do tempering at a slightly higher temperature. If you want higher ductility, you want to do tempering at a higher temperature. Or if you want the opposite property, you can just reduce the tempering temperature. So this just gives you an overall idea how the property changes in carbon steel. In other alloy steel, the trend and the value might be slightly different, but looking at the overall picture, this is how the properties change when you do heat treatment of carbon steel. I already discussed about this, so we won't go in the details of these. Yeah, then there is one really important diagram, which is called the TTT diagram, time temperature transformation diagram. I will quickly go through this, it won't take much time. Basically, this diagram is showing you that if you have steel, which is heated above AC3, so you start here. Now, how do you determine what phases should be forming? Do you want martensite? Do you want partial martensite and partial perlite? For that, you'd have to refer to the TTT diagram. This diagram just shows you that how you should be cooling in order to form what phase you need. So, for example, you have heated it above AC3. This red line is showing you the AC3 temperature. Now, if you cool the material in such a way that you don't cross this nose of the curve here, you cool it and then you reach here. That means with this cooling rate, I'm going to form 100% martensite because I did not cross this nose. If you cross this nose, you will form perlite or austenite. If I do cooling fast enough, that means I can form 100% martensite. If I do a slightly slow cooling, let's say I let it sit here for some time and now I do cooling, now I have some amount of perlite and whatever is the rest becomes martensite. So this becomes a really important diagram to understand. Whatever grade of steel you're working with, every grade of steel, if it's a standard grade, you will have a TTT diagram in the literature. Refer to that diagram and that will help you to do the kind of heat treatment you want to do. If you want to form martensite, if you want something really hard and strong, now you know how much time you have to form martensite. For example, in this case, like here, it's just showing you this is time in seconds. So you have like almost 1 second to do the heat treatment. So you want this complete piece to cool down in less than 1 second if you want to form 100% martensite, which is really challenging because if you have Thor's hammer, which is a really thick piece of metal, the interior cannot be cooled that fast. So you will form some perlite or some other phases. So, and this is just an example. Most of the time, you have more than 1 second to form 100% martensite. Depending on what's your requirement, you can do that kind of quenching and cooling heat treatment. So this is something which you should refer to if you're working with any standard steel. If there's no standard, then you might not get this plot there. Like for example, AF96, uh, they don't have the standard out yet, I feel like, or maybe they're working on it. So that's why you don't know much about that steel. Okay. If you want to make part of the material stronger, you can do a localized heat treatment. For localized heat treatment, you can either do flame hardening. That means you heat the material in a small region and then you quench that, then move ahead and quench it. And then you just don't do it on the whole material. That will give you a localized hardening, which sometimes is desired, sometimes it's not desired. So if you want some localized strength in a particular region, you can do flame hardening, right? A lot of time, like for gears and other equipments, you do this localized heat treatment because you want some ductility inside the material, but the edges, you want them to be really hard. So you can do this kind of flame hardening or localized heat treatment to get the desired properties. Induction hardening, it does the same purpose. So that is also a localized heating process. Diffusion, I already explained you about the diffusion, so that basics, I'm not going to go into it. If you need more information like how we do case hardening to get carbon diffuse in the material, if we go with that route, then definitely we can discuss this in detail. So yeah, this is just showing you some of the testing techniques that are available, which gives you different kinds of hardness on the material. So we'll discuss that as per our need. And now I just have one more slideshow, which should not take much time. If you have any question in the meanwhile, you can let me know. Okay.
So you said that
Yeah.
Bainite probably wasn't what we wanted. Why isn't it what we wanted or might want?
Oh, for
Because
bainite?
yeah,
Yeah. So
Bainite.
no, the thing is, it's not like bainite is something which we don't want. The thing is, for most of the application, uh, bainite phase doesn't give you drastically different properties for most of the cases. For some steel, for example, there's a kind of tool steel H13. In that the bainite phase gives you good property. So bainite is basically it it is a phase which is really similar to perlite. So perlite has a lamellar structure. Come on, yeah. So perlite has lamellar structure. Bainite is similar in the structure. It just is little finer than perlite, and the changes in property that bainite gives is not that like it's not that different than perlite. And the biggest challenge why bainite is not talked about so much is I showed you the TTT diagram, right? You have this here and you have like this. So this is what I showed you, right? You form perlite at the top, you form martensite at the bottom. This is a typical structure, TTT. Let's say you want to form bainite, right? So if you want to form bainite, the TTT diagram looks something like this. It gets complicated. TTT diagrams can be super complicated. So it can get like something like this. Then there'll be discontinuity. Then you have this region here. Now, what happens is bainite will be somewhere here. Like it's way on the right side. This is your time axis. So in order for you to be able to form bainite, what you need to do is like beam the austenite, cool it down, determine the temperature. This is ms. So you want to stay above ms and just sit there for do the heat treatment at that temperature for a really long time, and then you will be able to form some bainite in your steel, and then you just cool it. So bainite in most of the steel, it's firstly hard to form. It does not give a really drastically different properties. So people didn't focus so much on bainite for practical industrial application. From research point of view, people are doing a lot of research on bainitic steels because there are certain specific properties that bainite phase can provide. So now people have got really interested into studying the bainitic steel, and they're trying different methods to make this process easier, the formation of bainite uh, easier. So yeah, I mean, for our project, maybe we can look into the bainite phase. If it firstly, we need to decide which alloy we're going to use, and then once you decide the alloy, then depending on that, we can look into the literature if the bainite phase is giving us some advantage or not, and then we can see like, oh, bainite might be good, so maybe we can try that kind of heat treatment. That makes sense, Grant?
Yeah, that makes sense.
Okay, cool. All right, so this one test, which is called Germany test. I'm not going to go into details of this test. This is basically a test which people do to measure hardenability. Hardenability is different from hardness. Hardness is basically how hard your material is. Hardenability is the ability of a material to form martensite. So that means if you're quenching it, you form martensite, right? So depending on how fast you are quenching, how much martensite you are forming in different regions. So this is one test, Germany testing. Uh, just quickly, what they do is like if you have a piece of metal here, uh, yeah, you have a piece of metal here, and you're cooling it from the end. This region is fast cooled, whereas this region will be slowly cooled, right? Because you have the water source at the bottom. So here you have martensite, and then the amount of martensite form will keep on reducing. So then you just measure hardness of different region, and that gives you an information that how much martensite is forming, how easily my material can be hardened. And that's what hardenability is. We are not measuring that right now, so I'm not going to go in the details of this. Won't bore you guys with this information. But this is definitely a good property. Let's say we end up doing this kind of heat treatment and measure hardenability, then I'll explain details about this to you guys. Okay, I won't go into details of different kinds of steel. Oh wait, I'm not gonna go into steel. Yeah, sorry guys. There's one important slide which I didn't show you. Yeah, well, I'll just stick to this one. I won't go into tool steel detail. I think you guys can study that. Okay, so this slide here, I want to discuss this one. This basically, when we talk about steel, till now what we were discussing was carbon steel. That means the steel has just iron and carbon. Now you can add a lot of alloying elements and form different kinds of steel. So carbon steel, we discussed that. You can have alloy steel. Uh, Let me say that. Anyway, so you can have alloy steel where you have different alloying elements that are added to the steel. Then you can have something called HSLA steel, which is high strength, low alloy steel. You add only small amount of alloying element, but those elements are engineered in such a way that you get really high strength in the material. Really good kind of steel that we should keep an eye on. Then there are some tool steels. We can use some tool steels. Maybe that might be helpful for the project that we are looking at. These are different grades of steel that you guys should definitely be looking into. We have some mill heat treated steel, and then there's ultra high strength steel. There, it's not limited to just these categories. There are a lot of other categories as well for steel. These are just some of the major categories. There's like miraging steel and a lot of steel. Some steels are, they don't belong to any of these. Those are like proprietary material and they have their own naming scheme. So the numbering system for these steels, you guys might see 1030, 1040, or 1180 or something like that. So I'll just briefly explain you how you can identify whenever you see those kind of numbering. In case of steel, the numbering system followed is either the SAE system or the AISI system. The system is an old system. People nowadays, no, but I mean, it's an old system, but everybody uses this. But internationally, they have developed some other systems as well. But these systems are really useful, so everybody is still using this. In this system, you will have steel either with 5 letters or numbers or four. So you'll have 5 or 4 here. Now, in this, the last 2 digit, which is shown, either this or the 5 one, and the 5 also the last. So the last 2 digit tells you how much carbon content we have. In case of a carbon steel mostly. How much carbon we have is shown by this. And the first 2 digits, they at the very instant, they don't give you a lot of information. But if you know the system, they tells you which alloying elements are present. But that's something you would have to know. For example, if you have 10 in the first 2 digits, that means it's a plain carbon steel. There's no other alloying element. So if you have 1040, that means you have, this is a plain carbon steel, and this 40 basically means 0.4% carbon. So at a lot of places, steel percentage is shown like this, like 1% of carbon is shown as 100 points. That's also an industry standard people use. So if you have 40 points of carbon, that means it is 0.4% carbon. If you add sulfur to the steel, because sulfur provides certain properties, then the steel naming system will become 1 and then you followed by carbon percentage. So this shows you 0.3% carbon is present in my steel. Similarly, if you have a lot of alloying elements, forget about this book edition, like this was just for the class. So if you have, let's say, 4140, 4130, these kind of steels, that last 2 digit is still giving you information about the carbon content. It's obviously not an exact carbon percentage, so that's why there's a range. And then the first 2 digit gives you information about what other alloying elements can be present. So if you have a 4000 series steel, which is like 4 followed by numbers, That 4000 series basically tells you that it has chromium present in it. All the 4000 series will have chromium, and along with chromium, depending on what numbers you have, the alloying elements change. You have manganese, molybdenum, and nickel, and other material which are present. So that's your 4000 series. That's how you show the steel which is present. Sometimes the steel might have a prefix which says E. So you might have E4340. That just shows you that, okay, it was made in electric arc furnace. That's something which, at a bigger industry scale, people are interested in knowing how my steel was made. And if the composition changes from the normal composition, you'll have an X. That means it's not exactly what we were aiming for. We got close to that number. So that's what the X number shows you. Sometimes you have an H at the end that gives you information that, oh, this hardenability requirement will be met by this grade of steel. Any steel that shows you this kind of information, like which says that, oh, it has this for sure, or it behaves like this, it's going to be expensive. Any steel that has undergone such a rigorous testing, that will be expensive. So it just adds on to the cost of the material. A lot of time people have boron or lead added to the steel. So if boron is added, it has been shown by a letter B in the middle of the naming scheme. So you have XX, B, and then XX. Or if you have lead added, there's like L in the middle. Different alloying elements that are added impart different property. So that's why knowing the naming scheme becomes really important. At a lot of places, people started getting confused because all these systems that I discussed, this is the American system, and they wanted something which internationally will be accepted. So ASTM came up with a numbering scheme. It's a good numbering scheme. People don't follow it so much. Just stick to American number system. It gives you tons of information. But just in case you see some other grade or other category of steel, that's probably an ASTM standard, which is a combined. And if you combine ASTM and SAE system, it is called UNS system. It's it's not important. You don't have to know that information. All right, then there are like different kinds of steel. You can get like hot finished or cold finished. And we won't go into the details of this. Uh, yeah, this weldability. We're not welding, so I won't talk about that part. Yeah, you can add different alloying elements to your steel. I think this might be something which should be helpful for you guys because we're still in the alloy development stage. So let's say you want to add something. So these are some of the general alloying elements that are added which impart certain specific properties. Aluminum. I discussed about aluminum and silicon. They are added to get rid of those air bubbles. It's called the killed steel, if you guys remember. So aluminum and silicon, the way they remove the dissolved gases, it's called the oxygen. It removes oxygen. It helps in something called nitriding step as well. It restricts the grain growth, really good property that you won't have really gigantic grains. It restricts that growth. And typically the percentage added is small. Not a lot of aluminum is added to the steel. So aluminum is helpful. Sulfur and phosphorus, it helps you to improve the machinability of the steel. And you generally don't add a lot of it, but it will reduce your weldability, ductility, and toughness. So there's a give and take. What property you want, based on that, you add that alloying element. Chromium. Everybody knows chromium is something which makes the steel stainless. So chromium is helpful. It improves the hardenability of the material as well. So these are certain property that is provided by the alloying elements. We have a lot of alloying elements shown here: nickel, copper, manganese, silicon. I can give you this information if you want. I can share this slide with you as well. That will give you some idea of what kind of steel you want to make. Don't add lead. That's dangerous. You don't want to work with it. So yeah, that's what we have. This is how the naming scheme works. And I think that gives you a good starting point right now. Now after this, like all the steels that I have on the first slide, where did it go here? You can look into these steels yourself and try to figure out what would be helpful or useful for you. You can look into stainless steels. Now for normal carbon steel, we talk about iron carbon phase diagram. For stainless steel, carbon is really low. It's like very small percentage. So for carbon steel, iron chromium phase diagram becomes really important. So you can look into that as well. If you want, I can help you understand stainless steel much better. Then we have tool steel and all other kinds of steel. But now I think with this discussion today, you guys might have some understanding of where to begin with, how to search for different kinds of steel. Something that Dr. Aryave might be interested in is if you're adding an alloy element, you want to look at the phase diagram of the material. So that means, let's say you say, I want to add aluminum. How much aluminum do you want to add? To get that information, you will have to look at the phase diagram of iron and aluminum. The best way to find phase diagram is go online. There are a bunch of database present. I think ASM has a database. I think it's ASM. They have a database. You just check there, enter the elements that you're looking for, and then you will find a bunch of phase diagrams. So that can be a technique that you can use to figure out which alloying element will work for this composition. And of course, we can get along with some of Dr. Ariave's students to help us with the thermocalc and calpat if we need that to model the alloy.
Can you put the slides, like just post us the slides somewhere? I don't know if you're able to do that.
I cannot share all the slides. I can share this last one. And I think the others, like I'm recording this video anyway, so I'll give it to you.
Okay, yeah, cool.
Yeah, I
But
don't
technically you can't share the slides.
Yes,
all right.
yeah.
You own your lecture, but you don't own the slides. All right, that's cool.
Yeah, I won't be like I can do a bunch of discussion with you guys if you find something useful.
Also a question I had was so my general understanding is that like on a TTGA diagram, the stuff further out to the right would be like closer to equilibrium, right? Because
yes,
that's long. So then I would expect that if bainite is so far to the right, why is it not on the phase diagram? Like what takes up that space? Kind of.
Bainite is also a metastable phase. I see what you're saying. It approaches towards equilibrium, but it is also considered to be a metastable phase because a lot of time, if you just let bainite sit for a long time, it transforms into perlite again. That's a good point, actually. I never thought from that point of view because it's on the further right side. So it kind of forms after a long time.
Because I would think that at lower temperatures than that, I don't know, than the AC123 line, that line, that you would be forming perlite, regardless of how long you kept it there, even if you didn't go all the way down to room temperature or something, or if
you actually form perlite. Perlite is just like a term given. It's basically ferrite and cementite mix.
Yeah.
So you do form perlite even if you're ahead there. And then like once you go in the details of this phase diagram, you'll hear things like proeutectite, cementite, proeutectite, perlite, and those phases. So that just shows you that, okay, we are on the right side of this region and we are forming perlite in that region. So yeah, it forms there. We just didn't go into details of that part here. But I really like your bainite question. I'm gonna look into that.
Yeah. What I had seen looking at different microstructural components is that bainite forms underneath the nose of the TTT. Yes. And so you have to cool down, but cool down enough so that you can still cross over into that underside of the nose, and that's when you're seeing bainite.
Yeah, it forms under the nose and on the right side. That's for sure. it's hard, and since it doesn't give you a lot of changes in the property, that's why not a lot of work was done. But yeah, that's something which we shouldn't focus on a lot right now. I feel like it's very interesting. It's a good question. It's a good point. And I'll look into that. Although it's not my research, but it's interesting to know that. I'll look into that. But I would say, like, to start, I think you guys can start looking into what alloying elements you can add to improve the impact strength of the material. Because for a hammer, I think figuring out what properties are important, and then since Dr. Srivastava is in the as the mentor for this project, it would be good if you can discuss, like, find out which material or fracture resistance. So anything which comes to failure where fracture is happening or crack growth is happening, that will be Dr. Ankit's forte, and he would want to see you guys talk a little bit about that. So try to find something which shows like least amount of cracking. That means it shouldn't be super brittle, and then the toughness value should be high. So just looking at those alloying elements, if you can find something which improves the toughness, that would be something nice. Or if it helps you to not get a lot of crack, that means it's not that brittle. That will also be helpful. Look into that. That would be, I think, a good starting point. And then I think some tool steels, some of the tool steels are really helpful. I didn't discuss that part, but like there are a few tool steels which is like here. There are some tool steel which are like shock resistant tool steel. It is used for making hammers. So I would say look into shock resisting tool steels. Uh, Basically, any tool steel that starts with an S in the name, that is a shock resistant tool steel. So it can be S1. I have S7. I had a small rod of
Who
S7.
was it who was gonna, one of us we had said was gonna try to research tool steels? I don't remember.
I'm gonna do that.
All right, yeah. So definitely, if
Yeah,
you
I'll
can be
look
like,
into
oh
that.
yes, the S series of tool steels, they're called shock resisting. And even if all you can do is say S1 is shock resistant because it has this microstructural feature, then that's wonderful.
Exactly. I mean,
Yeah.
that will just show that you guys did some homework, went
Yeah.
into the details. So that'll be helpful. And they'll be like, all right, you guys are looking into things, so we'll just help you then. Then they might suggest some things. I actually had a small piece of S7, but I gave it to another researcher. Wu, Austin, you know Wu, right?
I don't know who, but
No, you don't know Wu,
oh, Woo. I thought you
Korean
said know
guy?
who.
Yeah,
Yeah, I know Woo.
that's his name.
I
Yeah.
thought you
So,
said you know who, and I was like, I don't know who.
yeah.
You know
So
Woo.
I gave it to him. He needed
Thank
it
you.
for something. But yeah, I mean, even hot work steel like H series steel, we make tools out of H13, a lot of them. So H series is also something which you should look into. It's nice. And just not like if you search for this still, that is helpful. Look from the point of view of casting as well. If investment casting can be done, because I think TPM will be doing investment casting, right?
Yes.
Yeah, so look for that as well. Like, how can we cast this material? Just looking at, oh, this is helpful, but can we cast or not? That's another challenge. So look into those aspects. That'll be nice. Now you kind of have an idea. If you see some terms, you'll get an understanding. And yeah, once you search, if you want to have a quick discussion with me after that, feel free to reach out and I'll be able to help. But yeah, that's what I have, guys. I'm gonna
Well, thank you. Yeah, that was really
Yeah.
useful.
I'm gonna stop sharing.
Yeah, thanks. Thank you a ton.
Yeah,
Yeah,
so
but
Yeah.
any question or anything?
I think we